All right, we are back for another chapter, another topic, another new piece of material for linear algebra, and it's post midterm, and we're going to be getting into some fairly heavy material. So what I'm going to need from you is I'm going to need you to take my advice when I mention keep a vocabulary journal. I will do my best to ground some of this stuff. It can seem very abstract, very esoteric, but I'll do my best to find some analogies, some applications for us. But let's jump in. So the topic, chapter 4, section 1, section 2, is the topic of vector spaces and subspaces, and this is going to take me multiple videos probably to really ground this for you, really get you where I want you to be. But for right now, let me give you just the bird's eye view of what I'm talking about. And then I'm going to try to give you an analogy using Netflix of how you can think about vector spaces and subspaces. Okay, so ready? So the idea for a vector space, what you have is you start with a set of objects, right? So you have a set of vectors. And so you have a set of vectors and you have two operations, okay? So the idea is you can add. So right now, what are the two operations? You can add your vectors. So you have addition. And you have multiplication by scalars. Okay, so are you with me so far? That if you have a set of objects, right? You got a set of objects in front of you that are a set of vectors, and the only thing you're allowed to do with that set is two operations. You can add them, and you can use some scalar to multiply them. Does that make sense? Nothing else is allowed. So with just these two operators and this set, what we do is we build a list of axioms, right? Or rules. It's 10 of them. And the way you can think of it is, in order to be able to make a statement that this here is a vector space, then all 10 axioms must be met. Okay, now the way I'm going to start this subject matter is we're going to narrow the scope a little bit. Okay, so if you allow me, let me draw you a big circle, and let's just say here are all the vectors that are in your vector space, right? They all live in this set, this circle. Now, what I'm going to do is I'm going to just grab a portion of that set, right? And we'll call we'll call it W. These are still vectors, but this is going to be a subspace of your vector space. You can think of it as an analogy would be a subset of a set, right? Now, so what am I trying to say? I'm trying to say that I'm going to start with subspaces and then build back to vector spaces. I think it'll click. Are you ready? Now, what is a subspace? Well, hold on. So remember, vector space had 10 axioms, right? You would have to go through and check off one by one all 10 axioms to confirm that what you have, that set, is indeed a vector space. Now, a subspace, right, is a subspace of a vector space only has to verify 3 of the 10 axioms. So notice what I've highlighted here. So we have what we call, and I'll go through these. So there's only 3 axioms that must be met in order to say that your set is a subspace of some vector space. And, well, we're going to have this what we call closure under addition, closure under multiplication, and the zero vector has to be in your set. Now listen, as I said, this can be fairly abstract, and I can lose you and I can lose your attention right now if I continue reading definitions. So allow me to try to build you an analogy. Okay? If you push this analogy too far, it will fall apart, obviously, but it will help you. So the analogy is dealing with Netflix. So, okay, so now I have not Googled this in a while, but we can say, or at least at last that I did look this up, I believe that Netflix has somewhere around 15,000 movie titles. Does that make sense? So we have 15,000 various movies that you could choose to watch on Netflix, say. Now, what we're going to do is we're going to think about the vector space, right? So V is our vector space. Is going to be the set of all the movies on Netflix, right? So it's going to be the set of all movies, all individual titles. Okay, so in other words, what we have is V sub 1, that is some movie that you can watch on Netflix, or let's TV show, whatever, however you would like to think about it. V sub 2 would be another movie, V sub 3, etc. You with me? And we keep going until we have listed all, say, 15,000 of their movies. So far, so good. Okay, now, the way I'm going to explain a subspace is, let's think of it like this. Now, when you first sign up for Netflix, right, let's assume that you opened a brand new account right now. Okay, so clearly, they're not going to show you all 15,000 selections that movie titles that you could choose from, all at on the main screen when you first log in, right? They're going to have a list of suggested titles. Agreed? Now, over time, as you start to watch various movies, like for example, my children watch a lot of SpongeBob SquarePants, right? So over time, Netflix is going to start to adapt their selection, right? The movies that they bring to you on the home screen. They're going to start to adapt that based on your what they perceive to be your preferences, right? So if you watch a lot of dramas, you're going to notice, or action movies, you're going to notice that a lot of these titles dealing with drama or action are going to start to show up in your suggestions, in your suggested movies to watch. With me? Okay. So now I'll just use me, for example. Let's just say that we're going to let W represent my list of movie suggestions. That would mean if I were to give you my login ID and my password, you could log in right now, and what you would be looking at would be my list of movie suggestions, which is the way we're going to think about a subspace. Okay, let's go a little bit farther. Let's try to push this analogy as far as we can. Now, right now, I want you to think about what is it in this algorithm that Netflix has built? What is it that actually determines what movies they're going to suggest to me? Right? Let's think of it as So let's say these are the three, let's say various movies that I watched. Let's say V sub 1, V sub 2, V sub 3. These are my favorite movies or TV shows. And my question that I just asked you was what would play a role in these movie suggestions? Well, clearly, don't you agree with me? The number of times that you've watched, say, a particular movie or a particular genre of movies, and maybe even the time that's elapsed, that right from the last time you watched a movie in certain dramas, right? Don't you agree with me? So how could we do that? So look, let's say V sub 1. I should log into Netflix right now and see what they actually have on Netflix. But ready, it is SpongeBob SquarePants Volume 1, Season 1. And let's think about now, my children have watched these cartoons that season over and over again. Now, how many times they've watched, say, each episode or each season can be represented by the weight that you attached. So we would have a scalar attached to the vector, and that would help identify to Netflix the number of times you watched said movie, right? A certain movie. Now, the way we can think about it is we can think about Netflix is basically just setting up a subspace by taking all the movies that you've watched, and the scalars being the weights of the number of times you've watched it, and then what pops out of this is what we're going to call W. And that is what I see when I log in right now to Netflix. This W is my subspace, my suggested movies. Now, what I want to do at this point is I hope that at least clarifies how you can think about, you have operations of addition and you have operations of scalar multiplication. And the last thing I want to see if I can identify is how do we think about that property of the zero vector? Well, this is, so maybe I will see if I can come back to this. I don't want to try to push this analogy too far right now. So what we're going to do right now is we're going to practice, we're going to play a game. And the game is, I'm going to write a set, and we're going to see if we can actually determine if it is a subspace, right? We have, remember those three axioms? Closure under addition, closure under multiplication, and closure, and that zero vector. We're going to jump in. I'm going to read this question to you, and we're going to see if we can actually determine if this is a subspace. Ready? So let me read. So up top it says, which of the following subsets of R2, now hold on, you know what I mean by subset, right? So a set of R2 would be every single point in R2, right? That's every single point in two-dimensional space would be the set. But a subset of R2 would be just a particular region, right? A collection of points that are in R2. So let me read it again. It says, which of the following subsets of R2 are subspaces of R2? All right. So I'm going to make this list of axioms just a little bit larger. I'll put it here for now. So while we tackle example 1. Ready? So let's read. It says W sub 1, so this is the potential subspace, right? We don't know yet if it is a subspace, is the set of all vectors where x is greater than or equal to 0. All right, now, what I want to do right now is I want to shade which of these quadrants are we in? So think about it. The set of vectors, now each vector is its own point in R2. Now I'm going to shade the regions, right, the quadrants where x is greater than or equal to 0. So, all right, let me go ahead and highlight this area right here. And do you agree with me that if you're in quadrant 1, clearly all your x values are greater than or equal to 0, and if you're in quadrant 4, all of your x values are also greater than or equal to 0, right? So, all right, so you can now think about every point in this set is coming from this shaded region. Now, we have not answered the question, is it a subspace? So first, let's start with, so I'm gonna go through each of these. We'll start with the 0 vector. Ready? So let's see if we can agree that the 0 vector is in this set. Okay, so for sure, if it says all x greater than or equal to 0, so that means the origin is the origin is highlighted here, right? Because the way you got to think about the shading, it goes all the way to the y-axis, and it actually does include the y-axis as well, right? So because it's greater than or equal to 0. So in this case, is the 0 vector in our set? And we're going to say yes. So checked off. Our 0 vector is here, and that is part of our shading. Ready? Let's go to, we'll go to what we call closure under addition. Okay, now the game that you have to think about, the way you got to think about approaching this, is if you can first let me read actually. So H is closed. I'm reading part B, right? So my apologies. Look at me. So ready? Let me see if I can try that again. So H is closed under addition, vector addition. That is, for each vector u and each vector v, the sum of u plus v is also in H. Okay, now it says H, we labeled it W, but that's okay. That's don't get confused with the notation here. So let me get this picture out of the way so we have some space to work. All right, ready? So let me start by do a kind of a sloppy way of figuring out if it's closure, if you have closure under addition. So we're gonna, how about you help me? I don't know how you would help me, but help me choose 2 vectors that are in this shaded region. So vector u and vector v. Okay, ready? I'm just going to choose, let's say 2, 2. Right, that would be there. So over 2, up 2. And I need another vector that's also in this shaded region. How about, oh, I don't know, 1, 1. Let's make it easy. Okay, so now, notice what this axiom says. It says that for each u and v in that subspace, the sum of those 2 vectors also has to be in that subspace. So if I take u plus v. Don't let me lose you right now. Please, don't let me lose you yet. Do you agree with me that 2, 2 is in that shaded region? Yes? Do you agree with me that 1, 1 is in that shaded region? Now, what about u plus v? Right, so I would have 2, 2 plus 1, 1. So u plus v is going to be 3, 3. Is that also in that shaded region? Yes, okay. So now you're understanding what we're talking about when we say the closure under vector addition, but I said that this is a sloppy way of doing this because you can't just verify a single instance, right? In mathematics, we want to be able to say that this is you have closure under addition for every single point in this entire shaded region. So, right, do you understand that you can't just play the game of let me pick some points. Now, there's a caveat to this, but you can't play the game of just continuing to pick points that show, yes, okay, that's also in that shaded region. Then I pick 2 more points, let's say 4, 4, and 5, 5, and oh, okay, that's also in that region. The game is not played like that. Now, however, if you were to pick 2 points, right? So please listen to me. You can show that it is not closed under a vector addition by simply arbitrarily choosing points because you found one instance. If you can find one instance where u plus v is not in that shaded region, then that one instance would nullify the condition, right? So that's the same way in the sciences, right? So sciences are not in science you're not making proclamations of truth, right? You're just giving tentative results, like your best guess as of right now, given the data that you have. All right, always subject to revision, always subject to new data. That's not how we are doing mathematics. The way we do mathematics is we actually want to be able to say, for every single instance, all of u plus v is also in this shaded region. So how do we do that? Well, let me erase, and I'll have to show you how we're going to do that. So what we're going to do instead is let's pick u to be an arbitrary number, like let's say x sub 1, y sub 1. All right, and then what we're going to do is, so do you agree with me that the x value for this vector u is positive, the y value for this vector u is positive. Now let's choose a vector v. Okay, so anything that's in quadrant 1, right? Anything that's in quadrant 1 will have what? It'll have over here. Anything in quadrant 1 is going to have positive x values and positive y values, right? So you would have positive x values, positive y values for anything in quadrant 1. Now, anything in quadrant 4, let's think about the types of points that live in quadrant 4. Well, the x values are still positive, right? But the y values are negative. Okay, so let's use that to our advantage. So now that I'm going to, if I were going to pick another generic point for v, let's make the x value positive, but now let's make the y value negative. Okay. Now the question still stands. Is u plus v also in that shaded region? Ready? Let's do it. So u, we have a positive x value, a positive y value, and plus v would be a positive second x value and a negative second y value. Now, what are the potential results that could come out of this? All right, let me go ahead and set it up. So if I add the x values, this would be x sub 1 plus x sub 2. Now, and let me go ahead and do y sub 1, and this would be minus y sub 2. And now what we have to do is let's first let's look at the x values. If you have a positive x value and you add a second positive x value, are you still in this shaded region over here? Yes. Right? No matter what x value, even if you chose 0, right? If it's a positive x value plus a positive x value, in terms of your x values are still in the shaded region. Now let's look at the potential y values. Well, y minus y could be either a negative number, right, a positive number, or 0. Right? 3, if you could have 3 minus 3 would get you to 0, y is 0. 3, you could have negative 3 minus 3 would be a negative y value. And of course, you could have 3 minus negative, 3 minus a negative number. The idea is you would, even if you have a positive y value, you would be in what? You would be in this region up here. If you were to end up with a negative y value, you would be in this region here. And if you were to end up with, if they just canceled out, you would still be on the x-axis. But either way, we're good, right? Either way, we have closure under addition. All right, now, a lot of my language is somewhat sloppy. If this would be, I'm trying my best to give you an intuitive look at it, a geometric look at it. I hope that this makes sense. But let's play the game one more time, because we can't say that this is a subset or a subspace yet. We have one more axiom to verify. Ready? So what I'm going to do is I'm going to go ahead and free up some space for me. All right, and let's get back. I'll go ahead and draw the shaded region that we're dealing with. And now let's go to the last axiom, which is what we call closure under multiplication. Right, so closure or closed under multiplication. Okay. So now let me read that last axiom. So part C, it says H, or what we have, our set would be closed under multiplication by scalars. That is, for each vector u and scalar c, c times u is also in this space, right? So c times u would also have to be in the shaded region. All right, ready? So let's see if I can get you up to speed. So ready? Let's just pick a vector u. Oh, I don't care. Let's just make it easy. Let's just say it's 2, 2. And now we have two choices of scalars, right? our scalar could be a negative number or a positive number. So I'll make our scalar, one of our choices could be, let's say, 3. And the other choice could be negative 3. Okay. Now what we're going to do right now is do C times U. And what we want to do is make sure that C times U is also in this shaded region. Let's start with the first one. So if you had, we'll start with the positive scalar. So if you had 3 times 2, 2, where would you be? Well, 3 times 2 is 6. That would be at 6, 6. So let's say you would be maybe somewhere up here, right? So somewhere in the first quadrant. Okay, so in that case, that definitely works. 6, 6 is still in the shaded region. Now, the only thing we're going to do is we're going to change that C from the positive 3 to the negative 3. And let's see what that does. Ready? So let me erase. And let's see if we have, let's choose the negative version. So now I would have negative 3 multiplied by 2, 2. And let's do it. Ready? So that would be negative 6, negative 6. Hold on. Wait a minute. If you were to plot out negative 6, negative 6, you would be here, right? Do you see how you found a single result where the axiom of closure under multiplication did not apply, right? You were able to find a single result. And that single result is enough to throw out the claim, to make the statement that this W sub 1 is not a subspace of R2. You found one single instance. So you can't, in other words, you can't work your way you can't just continue to pick more numbers that verify your result. But one single instance of a situation like this, one single instance where you can show that the claim is not true, you can throw out the you can throw out the question. You can basically make the statement that it is not a subspace. All right, so my apologies. I know this is tough. It's a lot easier if I actually have you in front of me and I'm not crammed in this little tiny area of board space or little tablet space. But all right, let me see if I can. I'm going to erase everything that I've written, and we're going to try it again. So okay, so from my experience, the way this normally works is at first it's just very confusing to students, but then you kind of start to get the hang of it, right? You kind of start to feel a little bit better about what the question's actually asking of you. So let me go ahead and jump back in. Let's read part 2. So part 1 was not a subspace. Now part 2, it says the set of all vectors where x is greater than 0, greater than or equal to 0, and y is greater than or equal to 0. So what I want to do right now is I actually want to graph that. So if you were going to graph, you're going to graph all the points x, y. I'm going to shade all the points x, y where x is greater than or equal to 0 and y is greater than or equal to 0. I think you're going to agree with me that is quadrant 1, right? And it also includes the origin. And so we have the x and y axis. So we have all of this region here. Okay. So what is that? That is the subset of R2, right? That is just the subset of all the xy points. But is it a subspace of R2? Well, let's find out. Let's jump in. Now, we can see that we can see that the first axiom, the zero vector, has to be in the subspace. But you can see that, right? We definitely have the zero vector in our subspace. So now let's go to, so we verified part A. Let's go to part B. So now we're dealing with addition, right? Closure under addition. All right. So let's take a glance at some vectors that you could choose that would exist in this region. Ready? Well, vector u, no matter what point you pick, it's going to have be a positive x and a positive y, right? And for v, no matter what you choose, it's going to be some, let's say, some other positive x, some other positive y. So the question is, in order to say, is it closed under addition, is what about u plus v? Is that also in the shaded region? Well, x sub 1 plus x sub 2, y sub 1 plus y sub 2. If you pick a positive number and you add another positive number, you still have positive x values. And if you pick a positive y and another positive y value, you have positive y values. So for sure, u plus v would also be in that region, right? Now, you can always, if it helps you, pick two different vectors. Pick 2, 2, and 3, 3. If you add them, you would have 5, 5. And you can see how, that's just one example, but you can see what I'm talking about, how it meets the axiom. It is closed under addition. All right, now, let's do the last axiom, which is closure under multiplication. All right, so the way this works is you need one vector and you need a scalar, but remember you have two choices of scalars. Since a scalar can be any number c, so you would have a negative c, you would have a positive c. Let me write this a little bit better. So you would have, u, then you're going to need a c, then you're going to need a negative c, right? You don't have the choice of just choosing the positive version of the scalar. You have to have, it has to be true for any scalar to be able to say it's closed under multiplication. So that's an important point. All right, well, the way you can do this, if it helps you, we can start by the way that you should do this, right? The way that you should do this is, again, pick some x, pick some y value, and then use a c and a negative c. You don't want to pick numbers. You should be able to show this the proper way by using all positive x, all positive y values. Ready? But if we go at it this way, let's think about what c of x sub 1, I don't need to even label the sub 1 since we only have one vector. Think about what c times u would be, and think about what c times negative c times u would be. All right. Well, let's start with the first choice. So the first choice is you actually choose a positive scalar. So this would be a positive c times your x value and a positive c times your y value. Does that exist in your subspace? Well, a positive, and remember every number in quadrant 1 is positive. So a positive times a positive is still a positive. And a positive scalar times a positive y value is still a positive. So it works for a positive scalar. But what about a negative scalar? Well, I think you've probably already spotted it. If you do negative c times x, then negative c times y, well, now we have a negative x and a positive times a negative, so we have a negative x and a negative y. This puts us over in quadrant 3, right? If you pick a scalar that's negative, that puts us in quadrant 3. This fails, right? This fails to have closure under multiplication. All right, I'm going to go ahead and stop the video here. When I start this video up again, we're gonna continue practicing with subspaces, and I hope you see the game, and then we'll start to add to our definitions. See you in just a bit.